Welcome to this user guide and demonstration of a CoreSpecViewer workflow. First I'm going to talk about what CoreSpecViewer is. It's a specialized desktop application for hyperspectral drill core analysis. It provides an end-to-end workflow tool from raw scan data all the way through to geological interpretation of the data. It's designed for geoscientists and hyperspectral specialists and built around their specific workflow needs. It's an open source research tool, and the GPL3 license means it will remain open source and all derivatives must also be open source. We're committed to a transparent, extensible and reproducible product. I will go through the core capabilities during the demonstration, but for the design goals I wanted to build a no-code platform for hyperspectral core scans so people wouldn't be reliant on Python scripts for reusable data. It has full pre- and post-processing transparency and control over every setting used. This means it can have reproducible workflows and analysis, and it's also capable of whole level interpretation, 200 plus core boxes simultaneously viewed and interpreted, and it's committed to using open data formats. What CoreSpecViewer is not is a replacement for vendor software, Breeze, IntelliCore, Lumo, etc. That software remains essential for acquisition, calibration and highly tuned and certified processing workflows. The CoreSpecViewer is a complementary tool focused on research and transparent reusable workflows. It's not a general purpose image viewer, it's specifically for hyperspectral core scans. It's not a data acquisition system, it's designed to work with already acquired legacy data. I will now go through the features of CoreSpecViewer. CoreSpecViewer is an open source platform for end-to-end core scanning hyperspectral data interpretation and analysis. This is the user interface. There are 4 groups of buttons. The first group for operations on raw core scanning data. The second group are interactive masking tools for masking out the core box material for later processing steps. The third group are for visualizing and interpreting processed core scanning data. And the last group are for visualizing and interpreting core scanning data at the whole level, multi-box operations. There are some global settings at the top: open, save, undo. There's also a catalog window, an info window, and the settings dialog. Because CoreSpecViewer was designed for transparent and reproducible workflows, we record all of the pre-processing settings, including the noisy edge band slicing, the smoothing parameters, and feature detection limits, and these are modifiable by the user. All other settings are modifiable in the codebase. This is part 1, a demonstration of the raw data workflow. When we click the open button, we're presented with a dialog that shows all of the different types of data CoreSpecViewer can open. The top 2 options are for working with CoreSpecViewer native datasets. This will be processed boxes and holes that have been created using CoreSpecViewer. The second 2 options are for loading raw datasets or radiance datasets in MV files. These will expect raw data cubes, white reference data cubes and dark reference data cubes. This option on the left is for a Lumo output directly. So this is from SpecIm acquisition software and will expect a certain file structure and hierarchy. This is for manually adding individual header files. It will expect a data header, a white header and a dark header. It will assume .raw prefixes on the binaries, but you can also directly browse to the binary files if your data has different extensions. The last one is for opening post-process reflectance. Many hyperspectral operators will provide reflectance data in an MV file that's already been corrected and potentially smoothed. If your data is smoothed, you can check this box and CoreSpecViewer will not perform any additional smoothing. If you leave it unchecked, it will assume it is pure reflectance data and perform smoothing operations. For this demonstration, we're going to use a Lumo output directory. This is a dataset provided by the Alberta Energy Regulator. They have an awful lot of open core scan data available for download, and this is one box as an example. When we load the dataset, it will use the white and dark references in the background to produce reflectance data using the settings that I showed in the settings dialog box. So this is a false color image of the reflectance data unsmoothed. If you double click on a pixel, you can see the unsmoothed reflectance data. In our raw tools, we have three options. The first is auto crop. This uses CV2 computer vision to detect a rectangle, so it may not work on your particular boxes if there are irregular box sizes or box shapes, or if you're scanning rocks as opposed to core, the auto crop function won't work. But we have a manual crop function as well, which allows you just to select a rectangle to crop out of your image. Once you're happy with your cropped image, you can click the process button. This will, as well as performing reflectance using the settings provided, produce a number of derived products and cache them. So it will produce a mask. As you can see, the mask is blank at the moment because we haven't given it any information as to what is not core material. It will provide a smoothed dataset, and it will provide a continuum removed dataset. In order to generate the core box mask, we have a number of tools under the masking heading. The first one would be new mask. This allows you to select a pixel, and it will perform correlation of the selected pixel against all pixels in the image and assign pixels with a similarity greater than 90% to the mask. As you can see, this has performed quite effectively. It's detected the majority of the cardboard pixels, but it has not correlated with a number across the top. We can use the enhance mask button and select a different pixel. This will perform the same process, adding the new pixel similarities to the mask. You can see around the edge there are a number of areas that have not been masked off. We can use our freehand mask outside selected, and just draw around the core area. To improve the mask. As you can see, this area up here is a bit speckly. We can use the despeckle function to improve the mask there, and there's still an area here that hasn't been masked out using the correlation or the mask inside. So we can use our mask inside selected freehand and just draw around the edge of our core. So there, with very little time spent and very few clicks, I have a decent mask. For this demonstration, I'm going to consider this mask acceptable. If this was a research project, I would probably spend more time improving the masking. But now that we have a reasonable mask, we can actually segment the image using CalcStats. This is CVT connected components function, and it produces a segments dataset. So this is segmented the box, and we can now use these segments to unwrap the box using the typical core pattern, top to bottom, right to left, and we can produce unwrapped data. So this is a concatenated image of the borehole in the depth dimension, and because our metadata includes core depth start and core depth stop values, we can do a per pixel depth registration for this image using unmasked pixels. Once we've completed the segmentation and the masking, our pre-processing is now complete, and we can use the save button to persist this to disk. It gives us the option of committing changes before savings. This is because everything we have done since we processed the data has been stored as a temporary dataset, allowing use of the undo button if we made a mistake in our masking. In this case, we're happy with our results, so we will commit the changes and save them to a directory. This act of saving will take all of these products and persist them to disk as an MPY file. That's the NumPy native binary, and it will also persist the metadata as a JSON, so open data formats will be fully available. The other advantage of doing this is when we open this data in the future, CoreSpecViewer will lazily load all of the MPYs as NumPy mem maps, so we will preserve our RAM and we can have many boxes open at once, which will be useful when we get onto the whole depth. So that concludes the pre-processing. In part 2, I will talk about some of the interpreting and visualizing tools on pre-processed data.